Hi, everyone. Hey, let's take a look at aldehydes and ketones today. In this video, we're in the middle of Unit 2 of our key concepts. Let's go to Key Concepts, Unit 2, Part 2. We're actually halfway through that already. Here it is. Cool. All right. So your document looks a little different. I decided to decorate this a little bit. Where's my pen? There it goes. I put this graphic here, a little more eye-catching, but hey, if you found Unit 2, Part 2, it begins with the reaction of epoxides. We covered that in the previous video. So then what you want us to do is scroll down till we can see some aldehydes and ketones show up. Quick little summary, right? Aldehydes, the R group can be anything, a hydrogen, some alkyl groups, alkanes, or a benzene ring. And the benzene can be decorated with other things, an aryl group or an arene. Same is true for the ketone. Doesn't have to be symmetrical. Doesn't have to have the same two groups on the other side, but they must begin with the carbon atom. That defines a ketone. All right, new functional group. What's our pattern? First we name it, then we look at special properties, then we look at how to make those functional groups. Then we talk about how to take those functional groups and change them into something else. Here we go, naming. And then when we talk about namings, we have to deal with the past that doesn't seem to go away, the common names. Well, thankfully, there's only two common names that are required in this course. One for a ketone, and that's acetone, which you may know as nail polish remover. Simply put two methyl groups on either side of the carbonyl group. We'll talk about carbonyl in a minute. C-double bond to O with two methyls on either side. That's acetone. And then formaldehyde, we saw that already. That is how you make a primary alcohol from a Grignard reagent. You must use formaldehyde. So in a sense, I'm hoping you already know this one. And yay for memes. If you see any clever chemistry memes, send them my way, please. A student a couple years ago sent me this one. Two common names, memorize them, know their structures and their names. And I think we got half of them covered already. Nice. All right. Something else from the past. So I thought I'd put it in here. Back in the common names, they didn't number their chains. IUPAC was the first to start numbering chains consistently in a pattern. Instead, they used the Greek lettering system to identify chain carbons and ring carbons, but they did things a little differently. So I'm going to call this the Greek system for naming carbons or numbering carbons. Labeling, maybe it should be labeling. Oh, there it is. Labeling atoms using the Greek alphabet. Okay, the way this works, and yes, you need to be familiar with it. I'm not going to use it a lot, but it's a common way of doing things. You're going to see it in the homework. You're going to see it on the internet. And so let's just go through real quick. So if you encounter it, you'll know what to do with it. Okay. The way the Greek lettering system works is you first identify your most important functional group. So in this first structure here on the left, the most important functional group is a ketone. So I'm going to circle it. And I know there's a carbon that makes up the ketone functional group. That's part of the ketone group. You don't label that. After that carbon, you begin labeling alpha, then beta, gamma, delta, epsilon, eta, zeta, theta. I was in a fraternity in college. I was required to memorize the Greek alphabet. Anywho, you don't have to memorize it. You already know the first three. I'm sure you've seen it in chemistry, physics, math, alpha, beta, gamma. And it goes from the most important functional group. The very next carbon is the alpha carbon. And you can repeat the same thing on the other side. Yeah, that's not so nice. So yeah, if you have a ketone, there's two alpha carbons. They're the ones attached to the ketone. There's two beta carbons in this molecule. There's a beta carbon here and over there. Weird, I know, weird. And then what can you do with the labeling system? Well, let's say you have your ketone and there's also an alcohol group. So which one's more important, ketone or alcohol? Well, the pattern in IUPAC naming, it's also the pattern in common naming pattern, whatever. More oxygens, more pi bonds, more important. The ketone has a pi bond. It outranks the alcohol. So the common way of naming this type of molecule, it's not a real official name for the molecule, it's the category you place this molecule into. It's a ketone. And then 2 carbons away on the beta carbon, right? Here's the ketone and beta's over here, but beta's also over here. On the beta carbon, there's a alcohol group. You kind of use a prefix name for it, hydroxy. So this is one type of beta-hydroxy ketone. And that's how you will see it being used in homework problems on the internet and stuff. They'll say, hey, we have a beta-chloroketone, or we have a beta-hydroxyaldehyde, right? So you just know beta is referring to 2 carbons away from the functional group. There's a functional group. In this case, it's hydroxy. The other thing you need to be aware of is the way they identified alkenes, carbon-carbon double bonds. Remember, a double bond is a 1 degree of unsaturation. So they said, hey, across the alpha and beta carbons, there is a degree of unsaturation. And why make it so complicated? There is a alkene across the alpha and beta carbon for this ketone. Yeah, they should have said alkene on the alpha and beta carbons, but nope, it's an alpha beta unsaturated ketone. That's the other common thing you're going to see. Okay, so now if you see a beta gamma unsaturated ketone, then you're going to go across the beta and gamma carbons to put the double bond there. Okay. And again, on the exam, for those of you who are starting to freak out because this is so darn weird, deep breath, just let it go. You don't have to use a Greek lettering system on any naming question on my exam. Nope, just use the common names. You only have 2 to worry about, acetone, formaldehyde. And if it's not those 2, jump and use the IUPAC system. It's much more straightforward than the Greek labeling system. Instead, the Greek labeling system you need to be familiar with so you can interpret homework problems. Ooh, maybe an exam question. Last example here, you may have heard of the building blocks of proteins, amino acids, sometimes called alpha amino acids. Those are the things that make up proteins. And that's because, well, what's the most important functional group of an amino acid? The carboxylic acid, more oxygens, more pi bonds. The next carbon over is the alpha carbon. What's on the alpha carbon? An amine or an amino. It's kind of the prefix name for an amine. Lysine is a little unusual. It's a specific amino acid that has both an alpha amine or amino group, alpha amino group, and on the epsilon carbon, there's also a second amino group. Anyways, that was just interesting, not on the exam. Okay, here's the important section you need to know about for nomenclature naming questions on the exam. The IUPAC naming system. So we're just going to keep the same set of rules, right? There's 6 steps. Find the longest chain, name it with the parent and the suffix. So you get some new suffixes here. That's step 2. Step 3 is number the chain, starting closest to the most important functional group. Steps 4 and 5 is you number and name all the extra groups, all the other prefixes. And step 6, you alphabetize those prefixes and construct your final name. Cool, so what have we got? Aldehydes. They look like this, or, you know, it could look like that, same thing. Ketones. They look like this. Okay, so if you have a molecule that you have to name and it has an aldehyde in it, and if the aldehyde is the most important group, use the al suffix, short for aldehyde. Okay, that has some logic, cool. Different molecule, you look at it, you inspect it, find all the functional groups, and you discover, hey, the ketone is the most important functional group. Out of all the functional groups, it has the greatest number of oxygens, greatest number of pi bonds. You decide it's the most important. Then you use the suffix -one, short for ketone. Nice, more logic. Later in Unit 3, we're going to look at carboxylic acids and esters and amides. They outrank aldehydes and ketones because they have more, well, the carboxylic acid and ester have 2 oxygens and outrank it. And the amides, IUPAC said, yeah, amides are going to outrank aldehydes and ketones too. So what do you do if your molecule has both an amide and an aldehyde, or an amide and a ketone? The amide wins the suffix. Well, then you have to use the prefix oxo. Wait, for both? Yeah. What? Well, if you see an oxo prefix in a name, how do you know whether it's an aldehyde or a ketone? Well, after you start drawing it, you'll figure it out. The oxo group refers to the oxygen double bond. And if it's in a prefix, there has to be a number in front of it. Say, where is that oxygen double bond group? The oxo group. And if it's at the end of a chain, that makes it an aldehyde, right? So here's my aldehyde group. And because the carbon must be attached to a hydrogen, aldehydes are only found at ends of chains. That's how you'll know the oxo group is referring to an aldehyde, as if the oxo group appears at the end of a chain. Ketones can't be at the ends. What defines a ketone? The carbonyl group with 2 carbons on either side. That will always place a ketone in the middle or somewhere within the chain. Can't be at the end. So I have to give IUPAC a little credit. We only have to remember one prefix for both aldehydes and ketones, oxo, short for the oxygen that's double bonded. And then we can figure it out whether it represents an aldehyde or ketone after we draw it. Cool. All right, let's see some examples and play this game, the nomenclature game. So let's name this molecule. Pause the video and give it a shot. All right, so step 1, find the longest chain or ring. Well, here are my chain carbons, and you do include the functional group that contains carbons. That's the IUPAC method of doing things. There's the parent. Step 2, let's name it with the proper suffix. Well, let's go after suffix first. What are our functional groups? We got halides. Halides don't have a suffix. It's just the fluoro group, which is a prefix. But this double bond O appears at the end of a chain. This double bond O has a hydrogen. That's an aldehyde. So we have to use the suffix al, short for aldehyde. Let's see, how many carbons are here? Well, 1, 2, 3, 4, 5, 6. 6 is hexane. So the parent is hexane. Think about using that E, but I check my suffix. Yeah, here comes a vowel. So I drop the E, and hexanal is the parent name. That was step 2. Step 3, number the chain, starting as close to the most important functional group as possible. Well, the aldehyde uses carbon number 1. That's as close as you can get, a whole 1. And then we number the rest of the chain, and the 2 fluorines end up on carbon 6. Step 3 done. Step 4 and 5, number and name with the prefix, all the extra decorations. Those are the 2 fluorines. You have to give both numbers. If you have 2 groups, or I tell my students, if you're using the di prefix, you better have 2 numbers. If you use tri, there better be 3 numbers, right? You have to identify each of those fluoro groups here, and there's 2 of them. So 6,6-difluoro is the prefixes, followed by the, whatchamacallit, parent name. Hexanal. Some of you are saying, wait, aren't you supposed to identify with the number, the suffix? That is a good habit to get into. And you have a choice of putting the number right before the prefix, or putting the number out in front of the parent. Both work. You'll notice I'm using parentheses. That's my way of saying, hey, this is optional. Why is it optional? Well, aldehydes are always or only found at the ends of chains. And if you're using the suffix, That makes it the most important functional group, which means it always has to be at the end or at the beginning, the most important functional group. You want to number it closest to that end. It has to be on number 1 if it's an aldehyde. So you can safely drop the 1 for your aldehydes if you're using al as a suffix. And if there's just one more thing to worry about, then ignore it. Put your 1s in there. It's not incorrect. It's just redundant. Just a little extra. It's not wrong, so I don't take off points. So all 3 of these names will give you full credit on my exams. All right, what else we got? Let's try this one. Let's zigzag like that. Cool. Pause video, attempt the name for that one. Well, the parent, the longest chain is right here. 5 carbons. Step 2 makes it pentane. Before I add the E, I think about, well, how do I identify the most important functional group? The ketone. So this is pentanone. That's the parent name. The end of my chain is over here on the left, over here on the right. Which one's closest to the ketone? The one on the right. So number the chain as close as you can to the most important functional group. So the ketone can never be on carbon 1. Only aldehydes can be on carbon 1. Right? Ketones are always found somewhere within the chain, never at the ends. If it was at the end, that makes it an aldehyde. What have we got? Prefixes and naming and numbering them. Well, on carbon 5, there's a chloral group. Actually, I'm going to squeeze in right here. I'm going to be lazy. And now that name would actually lose some points. Dang it. Why? Because the ketone has to be identified with a number. It could have been on carbon 3. The name of this molecule is still 5-chloropentanone, but this one, actually, it'd be from this end. Ooh. There's a tie. The ketone is on carbon 3, no matter which end you number from. So you break the tie by going to your first branch, which is the chlorine. So you put the chlorine on number 1. 1-chloro, 3-pentanone. Or you can put the 3 right before the one. This one we have to actually say, hey, the ketone's on carbon 2. And then I'll go the opposite. What's the word? Option. Instead of putting my 2 here, which you can do, you can put a 2 here now, or you can elect to wait until you get to the suffix and put your 2 there. There we go, 5-chloropentane 2-one. Nice. A couple more. Just make sure we're all in the same ballpark. Oh, what if we mix and match? Let's name this. Are you pausing the video? I'm watching you. No, I'm not. All right, what we got? Step 1, find the longest chain with the most important functional group. Well, there's only one chain. Let's see, there's 2 carbons here, 3, 4, 5, 6, 7, 8. Oh, okay, I got 8 carbons in my chain. There's the parent. Step 2 is to name it. 8 carbons is octane. And now, which suffix do I use? Well, what do I have? The double bond O at the end of the chain, well, there's a hydrogen here, making this an aldehyde. Double bond O within a chain, carbons on either side of the C double bond O, makes it a ketone. Who wins? IUPAC decided aldehydes are more important. So you have to remember that. And actually, they'll be useful when we talk about reactions. So aldehydes outrank the ketones. It's a tiebreaker. Okay, so octanal is the parent name with the proper suffix. Step 3, to number it. Well, we just said the aldehyde wins. So carbon 1's over here on this end, wherever the aldehyde is, right? Aldehydes are always at ends of chains. And then number the rest of those carbons. So the ketone showed up on carbon 6. That should be a 7. There we go. And so on 6, the ketone, bione, that's a suffix. We have to use the oxo prefix. And ooh, 2 O's together, that's weird. Yeah, it is weird. If you want to put a 1 before the aldehyde, or that might actually help it make it a little more legible. You don't, I'm putting this in parentheses. You don't have to do this. Oh, yeah, one more thing I'll get to in a minute. One idea at a time. You don't need this one, right? Aldehydes are always at the beginning of the chain if you're using the al suffix. But someone might say that looks weird. Is this oxutenol? No, it's oxooctanol. That doesn't roll off the tongue very well. 6-oxooctanol. Octanal. That was the second point. Stick your tongue out. Octanal. Be very careful on exams. You might want to exaggerate your A's, because if you have sloppy handwriting like I kind of do, and I don't see the little tail on the A, that kind of looks like an O, which indicates an alcohol. Darn it. So make sure your Al's are very different from your O's. Be careful when you're, writing your answers on exams. Please, make it very clear. I don't know if you have to actually go to capital, but I would say, oh, okay, I see it's capital A. No, just kind of exaggerate it. Octanal. Okay, that is a little more clear. It's an A, not an O. Thank you. Pay attention to those things. It makes my life easier when I'm grading. What do we got? Oh, wait, there's one more. Let's throw in a whole bunch more double bond O's in here. What else we got? I'll put one here. Okay, now what? Pause the video if you like. Step 1, longest chain. I should have counted as I was circling. Because step 2 is to name it. 1, 2, 3, 4, 5, 6, 7, 8, 9. Nonane. About ready to put that E here. Okay, so who's the most important functional group? Well, what do I got? Double bond O's at both ends. There's 2 aldehydes here. If you want, you can put those hydrogens in there to help you identify the aldehyde. 2 of them. Got 2 ketones as well, but the aldehyde wins, higher ranked. So if we had 2 chlorines, we actually had 2 fluorines earlier, and we used di in front of that. IUPAC says same pattern. We have 2 al suffixes, you're using dial. Oh, in that case, IUPAC says you might as well keep your E because a consonant's coming. So nonane dial is the parent name, apparently. Number to change, step 3. Start the end closest to the most important functional group. Well, number 1 could be on the left, number 1 could be on the right. They both hit an aldehyde, need a tiebreaker. Next functional group, if I start on the right-hand side, I get to a ketone right away on carbon 3. So that's the tiebreaker. Go to your next branch. Okay, so what we got? That was step 3, numbering chain. 4 and 5, steps 4 and 5. Number and name, the extra decorations. We have a bunch of ketones. Each one's an oxo. We got 2 oxos, so yeah, it's a dioxo. Wait, what are those 2 oxo groups? That looks funny. Make it a little more clear. They show up on carbons 2 and 4. Stick in front here. Now, if you're like, wait, I have a suffix, I want some numbers, you can throw in the 1, 9. You don't have to though. If it's a dial, 2 aldehydes, you mean the only way they can be existing in this molecule, carbon can only make 4 bonds. Aldehydes have to be at the ends. So it's nonane, well, it has to be on 1 and 9. If it was octane, it has to be 1 and 8 if it was a dial. Yeah, so you can leave out the numbers for your aldehydes if you wish. And most people do. So if you're comparing your answer to the answer key or on the internet, you're not going to see those 1 and 9 with the L. Cool. All right, there's one more special case IUPAC dealt with. Some of you were reading your key concepts and said, hey, Dennis, don't forget this little note here. What's that all about? It's a way of simplifying names. So let's scroll over a little bit. What happens if you have an aldehyde attached to a ring? Well, what if you wanted to create an aldehyde in a ring? So I want my aldehyde here, and then I want it in the ring. I want that aldehyde to be a ring carbon. Did anyone just flinch? I hope so. It's like, Dennis, you just gave that carbon 5 bonds. So no, aldehydes can't be within a ring. Can't do it, but you can attach them to a ring. Let's make a letter C here. And then let's put a chlorine over here. Oh wait, I have a better example. Let's put an ethyl group here and put a hydroxy group here. Yes, that matches my notes. Okay, so what if we have to name this molecule in an exam? Step 1, find the longest chain with the most important functional group. Well, we have chain carbons. This carbon is a chain carbon. It's not part of a ring. And then we have ring carbons. Ring carbons cannot be chain carbons. Remember that little sub rule back when we were naming? Yeah, so we have a ring of 6 versus a chain of 2 versus a chain of 1. Which chain or ring has the most important functional group? The chain of 1. Yuck. So IUPAC would say, well, the parent name is methane, a chain of 1, and then use the right suffix, methanal, methanal, and then number that chain. Well, it's carbon 1 of methane, and we used up all our numbers. Well, how are you going to tell where the ethyl and the hydroxy group is on this ring of 6? They say, okay, wait. This is goofy. Let's stop. Let's do something different. If an aldehyde appears on a ring, as it does here, we're going to switch to a new suffix. There's a carbon, a carb, that's not part of the ring. It's holding an aldehyde group. So let's use that suffix. Okay, in that case, the parent becomes the ring. So that's your ring. That's the parent. And that's the key. So the ring is called cyclohexane. And I'm about ready to put the E on here and name my suffix. Well, it's not going to be Al because the ring carbons cannot possess an aldehyde carbon. But there's an aldehyde attached to this parent. So IUPAC said, yeah, use the suffix carbaldehyde, which starts with a C, a constant. So we're supposed to leave the E in there and use carbaldehyde. What a long name. The parent name is cyclohexane carbaldehyde. And wherever the aldehyde, the suffix, that's where you start numbering the ring. Sweet. Well, not so much the name, but the numbering is awesome because now we can identify where the ethyl group and the hydroxy group are located. Okay, so which way do we number? Counterclockwise or clockwise? I picked this example just to highlight one of the nuances of the IUPAC rules. I should have popped it up on the screen. You can look it up in on Canvas. You can find the nomenclature rules, and either in the assignment or in a previous assignment on naming. The names, let's see, we're at step 3. Number the longest chain or ring with the most important functional group. If you have a tie, you break the tie at the next branch. Not the highest rank, next ranked functional group. No. Next branch, next functional group or decoration. So if you're here on carbon 1, do you want to go over here to 2 or do you want to go down here to 2? Well, there's a branch up here. So that's how IUPAC plays. Find the suffix with the highest ranked functional group. But when you're numbering, If you have a tie, you go to the next branch, no matter what it is. Don't look at its ranking. So the ethyl group, it doesn't outrank alcohol, but that's not how the game's played. You start right here where the carbaldehyde group is on carbon 1. Go to as quickly as you can to your next group or branch. So we're going counterclockwise. Cool. That was step 3, number the ring, the parent. Step 4 is number and label extra groups. Well, on carbon 2, there's an ethyl. And on carbon 5, there's the alcohol. Wait, don't use the ol suffix. Suffix is a reserve for the highest ranked group. Aldehyde already claimed that with carbaldehyde. So sorry, alcohol, you've been demoted. You have to use a prefix name for you, and it's hydroxy. It looks like a hydroxide. No charge on that oxygen, but if it did, it would be -1 hydroxy, hydroxide. That's how I remember it. Cool. We got 2 prefixes. Alphabetize them E before H. So 2-ethyl, 5-hydroxy, cyclohexane carbaldehyde is your name. Whew. And we are done naming. Yay. Let's go see some reactions. Let me double check though. Yeah, nothing down there. Excellent. Okay, it's a short list of reactions, thankfully. I feel like we're missing something. We are. There we go. Excuse me. Let's talk about how do you make aldehydes. You synthesize aldehydes. We already know. I hope you remember. Take a primary alcohol and you use pyridinane. That insane pyridinane. If you need a structure, think of a benzoic acid. Don't add the H. Put an iodide here because IODO is iodo. That's iodine kind of in there. So put an iodine here. Link the O to A and then add 3 acetate groups. Again, you don't have to memorize that structure. You just need to recognize it in case I draw it on the exam. Because when I write my exams, I can choose either to write out the word pyridinane or I could draw its structure. If you're giving the reagent, you get to pick. You could draw the structure or you can give the name. Either one works. And with this mild oxidizing agent, you double up the bond, take away the H, and we have our aldehyde. That is the best way. Start with a primary alcohol of your choice, oxidize it gently to an aldehyde. Cool. There is a new way. It can be useful if you have an ester. So let's, where do I got my notes? Yep, I got that one. Okay, there's this new reagent called diba, or sometimes it's called dibol H. It's used in 2 steps. Step 1, first reaction, add the reagent diba. Or if you want to spell it this way, dibol H, you can. And then you always add hydroniumide. And what happens is you just clip the ester right at the single bonded carbon oxygen group. And your 2 halves. One's an aldehyde. That's what we're trying to do, trying to synthesize the aldehyde. And then the other piece is an oxygen with a methyl group. And wait, this oxygen, these 2 bonds, H plus supplies it with an H. Most people would draw that molecule as methanol, CH3OH. Same thing. Your choice. And then there actually is a hydrogen here. It actually comes from diba. Okay, so that's the reaction. I know it's a little weird, but let's make it a little more familiar. The reagent diba stands for DIB, diisobutyl. So right here, that looks weird with those methyls. So if I put the aluminum here, yeah, I have a isomer of butane, isobutyl group, and then you're going to do it twice. So here's another isobutyl group, and I connect it over there. 2 isobutyl groups on aluminum, diisobutyl aluminum, And then the third bond to aluminum is hydride. And that looks really similar to lithium aluminum hydride. Wait, lithium aluminum hydride reacts with esters too. So let's take the same, oh, let's actually give ourselves a little more room. Nah, we got started. Sorry, I'm being a little wishy-washy. Okay, when you use lithium aluminum hydride, when you use a Grignard, when you use sodium borohydride, and when you use Dibah, you always have an acid step, second step. It could be just H+, could be sulfuric acid mixed with water, your choice how you want to draw the acid form. Most of the time, it'll be hydronium. And what happens with lithium aluminum hydride, you actually get a pair of alcohols. Let's review the mechanism so you don't have to know the mechanism. Okay, you don't. That's what it says. But it happens to be the same one. Some of you enjoy, that's probably the wrong word. Some of you find value in knowing the mechanisms because it helps you predict products. I do too. So let's run through the mechanism for lithium aluminum hydride. And we'll get a better understanding of what this Dibah is doing here. Okay, so the mechanism of lithium aluminum hydride and esters. Another methyl, another carbon over there. What we said is that lithium aluminum hydride supplies the hydride ion. And the hydride ion goes after the most positive atom here, which is this carbon, at the link to two electronegative oxygens. And so the lone pair bumps up the pi bond. That's what the Grignard did. Yeah, lithium hydride, sodium borohydride do the same thing. So the hydrogen attaches to the carbon, but carbon says, whoa, I can only maintain 4 bonds at a time. So the oxygen says, no problem, I'm more electronegative. I was trying to tug of war, pull these bonding electrons away from you, carbon, and I succeeded with one of the bonds. And now I have an extra lone pair, right? The ketone oxygen had 2 lone pairs, a double bond. And the first step of the mechanism not only has 1 covalent bond, but 3 lone pairs. And then what we remember from both the Grignard reactions and the lithium aluminum hydride reaction, the lone pair comes right back down to double up the bond. And now one of the other 3 groups has to leave. So the carbon maintains 4 bonds. And the weakest link breaks. The weakest bond links, the weakest bond breaks. And that's the one between the carbon and the oxygen. Oxygen's more electronegative, pulling on this bond, weakening it, and it snaps, pops off. So then we have the double bond, we have this hydrogen, and then we have the negative oxygen still holding on to the methyl group. We made an aldehyde. And back in the previous video, we said, wait, lithium hydride also reacts with aldehydes as well as esters. And in fact, aldehydes are more reactive. We'll discuss why at the end of this video. So another hydride ion comes in. Well, there's 4 of them available, plenty of hydride ions available. So another one comes in and does the same thing, bumps up the pi bond. So there was 1 hydrogen already, the second one came in. We still have that negative methoxy group. And we're done with reaction 1. Lithium hydride is spent, right? This oxygen thinks about dropping the lone pair, making a double bond, but then it'd have to kick out H-, ooh, powerful base, or this carbon have to leave with a minus sign. Ooh, carbon, yikes. Those are the most powerful bases. They're very unstable. It doesn't happen. By the way, that's going to be a recurring theme. We'll also review that later in the video. In the ester, that pi bond did come back because we had another group that could take away the negative charge, right? This oxygen has a negative charge and this oxygen says, no, I want 2 bonds instead. makes a double bond, kicks out this group. Aldehydes and ketones, there are no electronegative atoms that could take away the negative charge. That's the big difference. One of the big differences between aldehydes and ketones and anything else with a C double bond O. More on that soon. Let's see, step 2. Well, step 2, the lithium hydride reaction is add H+. And let's add it twice. Here's hydronium, here's hydronium. We do have an excess of acid because all the negative oxygens want an H+. This one becomes a primary alcohol, and this one also becomes, well, I guess it's primary. Is it 0 order? I don't know. It's methanol. Done. Okay, where did diabol come about? Well, scientists knew about lithium aluminum hydride for a while. They also knew that aldehydes were being made in the course of the reaction. And a lot of them said, please stop lithium aluminum hydride. It's more of the aluminum hydride that's unstable and reactive. Leave my poor aldehyde alone. Stop it. Stop sending that second hydride ion to attack it. And so they said, well, why don't we just tweak this reagent and take away 3 of the H's? Let's just have aluminum with 1 H. That's what we have up here in diabol. It turned out it still is too powerful. You'd have 2 molecules of the lithium hydride attacking the aldehyde because aldehydes are just more reactive than esters. So the scientists said, okay, how can we weaken it further? We took away 3 of the 4 hydrogens. That weakened it a lot, but didn't do quite the trick. Well, let's put in steric hindrance. Let's bulk it up and make it crowded so it's less reactive. Well, they decided to go with the isobutyl groups. That's pretty crowded. And it did the trick. So they designed this reagent by tweaking lithium hydride, and they made diabol, diisobutyl aluminum hydride. And that's a reagent that will stop right here in the mechanism. So if someone asks you for the mechanism of diabol, it's the first half of the lithium aluminum hydride mechanism. Yay. Hydride ion comes from diabol. It stops here. We're done. Yay, aldehyde. Oh, you still have to add H3O plus. Give this negative oxygen. It's alcohol, right? It's hydrogen. Cool. Done and done. 2 methods on how to make aldehydes. Yeah, I still go with the pyridinane. That insane pyridinane. That'll be more useful. Ketones, still 2 ways, just like the aldehydes. And again, the first method, the old method, still the best. Take a secondary alcohol, hit it with a strong oxidizer. Or actually you can use pyridinane. Yeah, oh, good, there it is right here. So use an oxidizer, whether it's pyridinane or one of the strong oxidizers, because strong oxidizers with a secondary alcohol just stop at the ketone. And hey, that's what we're after. How do you make a ketone? One of the best ways is from a secondary alcohol and your choice of 1 of 5 oxidizing agents.